So the differential is that dy piece. And we said that is f prime of x times dx. That's just an equation. We are going to be calculating these things exactly, because if we have values for x and y, we can actually calculate f prime of x. Dy, your differential, we will find it. It's essentially saying what's the change in y. Okay, the differential is the approximation to the change. Then in the change in y that Riley was reading about, that is the actual change in y. So a differential dy is like saying the approximate dy is an approximate amount that y would change. It's like predicting the change in y. And we find it by using the change in y on the tangent line itself. If we look at this picture that Riley was reading about. So we have this point, xy. That is a point on the actual curve and the tangent line. It's the point where the tangent line meets the curve. This point right here is on the curve itself. They called that point x plus the change in x, just meaning x plus however much you increased it by. And the y value they called y plus the change in y. I'm going to run out of space. Just saying your y would go up, your x went up. Okay? If we are using the tangent line, is the point on the tangent line the same as the point on the curve? No. We know that as long as you're talking about 2 points that are relatively close together, it's not too far off. The farther we travel on this line, the farther it's going to get away from the curve. Change in y is the true amount that your y would increase on the curve itself. Dy is the amount it increased on the tangent line. And so the idea is, if you're picking an x value that's really close to the original point, change in y and dy will be very close to one another. As your x gets further away, what's going to happen to your change in y and your dy? Are they going to be close together or further apart? They're going to get further apart as well. Okay, let's look at an example. I want to compare the actual values of change in y and dy for this function. We're going to do it 2 times. Part A, we're going to look as x changes from 2 to 2.5. So the change in y is the true amount y changes on this curve. So to get that value, we just need the 2 y values for this curve itself, and we can subtract it. So I first need to find f of 2 and f of 2.05. So you plug those in. Get a 9 for that one. For the next one, I get 9.717625. So for the actual change in y, we are just going to subtract those. The ending y value minus the beginning y value. Bless you. So that's my true change in y. dy is an approximation to that using the tangent line. So we said dy is f prime of x times dx. What is f prime of x? Derivative of the original, so that would be a 3x squared plus a 2x minus 2. We are talking, if you think about our picture, x is the original point, so we're talking about when x was, you go with your starting point. So we went from 2 to 2.5, so we started at x equals 2. dx is the change in x. If you start at 2 and you end at 2.05, what was your change in x? 0.05. What if you started at 2 and you ended at 1.5? Negative 0.5. If your x gets smaller, it would be a negative. Okay? So now I can find f prime of 2. That gives me 14, is that right? Okay, so then to finish this, dy is f prime of x, which was 14, times my dx, which is like the change in x, which is 0.05, and we get 0.7. Okay, so this says the true amount y changed on this curve was 0.717625. If we used our tangent line to try to predict it, we would have gotten 0.7. So, not too far off. Let's do it again. This time I want to look at it changes from 2 to 2.01. So we need to figure out what we get if you plug 2.01 into the original. So my change in y this time, if you did, you'd have to do what? The f of 2.01 minus the f of 2, your ending minus your starting. So our change in y is 0.140701. dy would be f prime of x dx. The dx this time, we started at 2 and ended at 2.01. So if you subtract the ending minus the beginning, you get 0.01. F prime of 2 we've already done, that's 14, so our dy is 14 times 0.01, and we get 0.14. Okay, again, is my dy close to my change in y? Yeah, this is my approximation, my differential, and it was pretty close to the true value. Okay, if you had to compare these two, which one was closer, A or B? B is closer together. Why? The x's are close together, aren't they? The closer together your x's are, the closer together your y's will be. So I asked you to just compare those. So we see the change in y is close to dy. And the approximation is better. When the change of x is smaller. In other words, if there's less difference between your x's, there will be less difference between your y's. Questions on that one? Okay. Let's take a look at this. So, the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? In other words, you're talking about a sphere. You know when you measured the radius of that, it's possible you were off by 0.05 of a centimeter. So if you were, how far off will your volume be? If your radius was 0.05 off, how does that impact your volume calculation? So we do this using differentials. And we're talking about volume of a sphere, which is 4/3 pi r cubed. My radius we measured to be 21. dr is like talking about the error in your radius. What was the error? 0.05. Okay, when I want the maximum error in the volume, what I mean is find dV. Okay, a differential is like the error calculation. We know that dV is, if we use our differential formula, f prime of r times the dr. In other words, I need the derivative of this, and then I can multiply by my change in r. Alright, so let's talk about this derivative. If I want to do that, the 4/3 pi is just my coefficient. So if we bring that down, we get a 4 pi r squared. What r value am I going to be plugging in there? 21, so we have 4 pi times 21 squared, that's our derivative, and I need to multiply that with my dr, which was 0.05. Let's just put all this in our calculator. So the maximum error in volume is the 277.0885. Volume would be cubic centimeters. In other words, if you were only 5/100th of a centimeter off when you measured your radius, your volume is now 277 cubic centimeters off. So this process is used a lot in manufacturing. Now, if you're going to make a part and it has to fit, how accurate do all those measurements in the part have to be so that the final piece that you make will work for its intended function? All right, any questions there? Sorry, you could call it. I probably should have labeled that as prime of b. I think I've just, I don't know why I wrote r there, but it's a derivative of the volume. Thank you. Any other questions? So we are ready for the day 2, so it's the problems we didn't already do. Um, 35, the question in the book asks for a couple different things. All you have to find is the maximum error only. It asks for both the maximum and the relative error. I didn't talk about relative error, you just need to do the maximum. If I said, find the differential. Okay, I'm not giving you any numbers here, so you're not going to get a number answer like we did. So a couple ways you could do it. Probably the easiest is just thinking about it like I wrote up here, dy dx equals f prime of x. If I want to do this derivative, you know your f prime of x is 6x minus 5, so your differential dy, our formula is f prime of x times the dx, and that's all it is. So you're just writing the equation on this.